Drilling Info is happy to release the first version of an advanced property estimation workflow known as Ape. Using well log data from vertical wells and a 3D geologic model, Ape interpolates and extrapolates these data to any 3D location in the model using a variety of interpolation methods. This technique performs direct interpolation at any desired resolution, bypassing the need to build large and complex 3D grids and perform property modeling where upscaling averages out data. There are many applications for this workflow. We will show its application of building planned wells on open acreage and the estimation of a well log. Secondly, we will interpolate well logs to planned and existing horizontal wells for predictive MV stats workflows and post-mortem and live geosteering studies. To run the Ape workflow, simply select a candidate set of vertical wells with well logs. Select a well log alias or mnemonic well log to interpolate, and lastly, select a geological model from either a structural model or a stack of geologic horizons. That's it. You then construct the well grids. You can QC the interpolated results by picking a search and interactively observing the interpolated log at any given point in the model. The interactive spider illustrates what wells are contained in the search and the relative distances to those wells. The plot on the right shows not only the log, but the zonation of your stratigraphy at that location in the model. Once the desired search is set, you can digitize new vertical logs and wells anywhere on the map. Here, we propose a prefix name for the vertical wells that we will digitize. A 3D view is controlled by the workflow and shows the newly proposed vertical wells and corresponding logs. Here, we show how to interpolate well logs onto planned and existing horizontal wellbores. Simply specify a candidate set of wellbores to interpolate onto. Specify a sampling increment. Here, we use 1. Specify an interpolation algorithm and run the Ape interpolator. The results are shown in the bottom plot where you can thumb through all of the wellbores. When you are happy with the results, you can save them to the wellbore using the Save option. The Ape workflow was motivated from many of our customers from the need to interpolate well logs to various data objects in 3D. An example are horizontal wells, which typically have very sparse log coverage, but surrounded by many vertical and deviated wells with abundant log suites. The idea is to interpolate from the surrounding abundant vertical well log data to the sparsely populated horizontal wellbores. Typically, this is done by constructing large 3D gridded models and interpolating well log data to these grids as shown here. The drawbacks of such a workflow are illustrated here. Mainly, they are time-consuming, require specialized staff, over-average data, and can require large storages. The Ape workflow abstracts these important concepts, yet it is not burdened by these problems. The Ape workflow is launched under the Geology main menu item. It has a data setup page where you specify a candidate list of vertical source wellbores and well log data, a well log sampling rate that controls the resolution of the grids created along the wellbores, and a geologic model that is either a structural model or a stack of ordered stratigraphic horizons. There is a QC Well Grids tab where the results of the data setup are quality controlled and an appropriate search is set up for subsequent estimation. Lastly, as of the first release, is a Well Logs tab where the user specifies a set of candidate wellbores and an interpolation algorithm to estimate well logs on the wellbores. Back to the Setup tab. Here we specify a well list that has vertical wellbores and gamma ray logs. We leave the default sampling at 1 foot. Our first model will be built using a structural model approach. This is the most rigorous and easiest approach. Structural models are built in Transform structural modeling workflow. Here, this part of the workflow is similar to the well targeting workflow, except that you must also specify a stratigraphic layering type. We graphically illustrate here what this option does. When interpolating well log data inside a geologic model, the layering style of the stratigraphy is critical for how data is searched and found. It is important to note that you can only specify parallel base for the top zone and parallel top for the base zone to model the two unbounded half spaces. Next, we model using stratigraphic columns. Strat columns are created in Transform and they represent a stack of geologically ordered sequences separated by geologic boundaries, or horizons in Transform. After we choose a strat column, the zones are populated in the table. Note that the layering still applies in this approach. We digress for a second and launch the strat column workflow under the Geology main menu. The strat column is laid out with an editable canvas to the left and a table of horizons or geologic sequence boundaries to the right. You simply drag and drop the horizons at the right into the strat column on the left, making sure the horizons are in the correct geologic order. The table on the right allows you to set default data values for each geologic boundary. Note, this is critical to do to make workflows such as well targeting, velocity modeling, structural modeling, and now Ape much easier later on. Back in the Ape workflow, we rebuild the well grids using the strat column approach. If no strat columns or structural models exist, the user can simply select a set of horizons to add or replace what is in the table. In this layer cake modeling approach, the user is free to move these horizons up and down, essentially repeating what is accomplished in the strat column workflow. In the non-structural modeling workflows, there are two area of interest options available: the From Data and User Set options, which are reviewed here. The From Data option will set the 3D area of interest to be the extents of all the data, including wellbores and horizons. This is the easiest option, but you may interpolate well logs beyond what you intend. Again, we point out that the From Data option uses the entire extent of the data both vertically and aerially for the property estimation. The User Set option requires the user to set an aerial region polygon and a vertical region of interest. The vertical region of interest is controlled using a 3D graphical object shown here. If any of your horizons have holes in them, resulting say from seismic data or faults, we have added a new gap filling tool to easily fix these. This should be done to speed up the Ape interpolation. Here we show an example from the Teapot Dome field. It works on all of the horizons that are loaded into the table. As before, set the aerial and vertical AOI discussed. It is best to have the horizons shown in a 3D view to quickly view the changes. Once this option is run, All of the holes are filled and the horizons will extrapolate to the AOI boundary. All other data in the horizons remain unchanged. On this tab, we QC the results of the well grids built in the data setup step. At this point, all of the well log data from the vertical wells has been sampled onto a high-resolution grid along the well bores. Dragging with the left mouse button on the base map will show a spider-like graphic that represents a search. An octant search is used by default. All of the vertical wells found in the search are used to construct an interpolated well log shown at the right. By default, an inverse squared algorithm is used because of its simplicity and speed. You can change the type of search to change the number of sectors used. The num points option controls how many points are contained from each sector. Typically, an octant search with 1 or 2 points per sector will be used. Here we illustrate the effects of changing the search types. In addition to displaying the log at the right, the stratigraphy is also shown as well from the geologic model. Changing the min and max ranges determines how far the search will look for data. For example, in a cross-validation study, you will want to set the minimum greater than 0 to ensure that when estimating on a wellbore, it will only use data beyond the wellbore being estimated to. We changed the minimum back to 0 since we will now estimate new vertical well logs. To do this, simply click on the name checkbox, enter a unique name, and then shift left click on the map on the new proposed location. It is best to have a 3D view open as well with the appropriate data shown. The newly digitized wells will appear in the 3D view. Note that a unique number is appended to the name you specified. Also, note the accuracy of the well logs and the significant changes at the geologic boundaries. This is all guided by the geologic model. We now take the results of the well grids and the search and use these to estimate well logs on existing wellbores. We specify a set of horizontal wells using an inclination cutoff greater than or equal to 80 degrees. This will winnow down the wellbore table to horizontal wellbores that meet this inclination constraint. We then search for a set of wells, the Spanish Trails wells, by using the table search item. To make the interpolation go a little faster, we use an output log sampling rate of 2 feet. We run the inverse distance squared algorithm first because it requires no parameters. The results can quickly be QC'd in the lower wellbore log display. Note that there are some areas along the horizontal section of the wellbore where the log pattern is blocky looking. This results from horizontal wells that are very flat and parallel to the top and bottom horizons. Once you are satisfied with the results, you can then save the results to the database using the Create option. Here, you will need to specify a unique mnemonic name. We now show the results in the 3D view. We now show how to integrate seismic data as a soft trend when estimating well logs using a geostatistical technique known as collocated co-creaking. First, we change the interpolator type to co-create. We then select our soft data that was extracted to our wellbores from a seismic porosity volume. These are shown in the 3D view. We simply go back to the Data Setup tab and rerun the same model but with a porosity log now instead of the gamma ray log run earlier. It is that simple. We quickly QC the results on the QC Well Grids tab and look at our porosity trace. We will leave the search parameters unchanged. Back on the Well Logs panel, We leave the selected wells the same and change the correlation coefficient to 0.45 that we modeled in our MVStats workflow. We also change the X and Y variogram ranges to 4,000 feet and then run the model. We again quickly thumb through the estimated well logs in the well log display. We again assign these well logs a unique mnemonic and save them to the database. The estimated logs are now displayed in a 3D view alongside the soft seismic porosity logs used as soft data. The estimated logs are the higher resolution logs. The higher resolution is being driven by the porosity logs at the wells, but the seismic trend contribution is evident in the estimation.